Welcome to the deep dive. If you're gearing up for a senior software engineer technical interview, especially one diving into system design, you're definitely in the right place.
Yeah, happy to be here.
We're going to zero in on a critical area, distributed databases, and specifically the strategies around keeping them available and, consistent.
Absolutely crucial stuff for senior roles.
Landing that senior role isn't just about knowing the buzzwords, it's about showing you really get the trade-offs involved in building resilient systems. That's our mission today, right? To equip you with the knowledge to confidently tackle those tricky questions about database availability when, well, things inevitably go wrong.
Exactly. In those system design interviews for senior roles, your ability to reason about the robustness of the data layer, that's a major signal. Interviewers want to see that you can anticipate potential failure scenarios and understand how different database architectures handle them. Today, we'll be dissecting leaderless replication and the core concepts of quorums. These are fundamental building blocks for engineering truly resilient distributed systems. And understanding them deeply is, well, it's key.
Okay, so let's dive right into leaderless replication and these quorum configurations. One of the first things that jumps out is how these systems can handle individual server failures without needing a full-blown, failover. Can you walk us through the magic behind that?
Certainly. Imagine your data isn't on just one machine, but replicated across several. With a quorum configuration, you define two key numbers. A read quorum, often called R, which is the minimum number of nodes that must acknowledge your read request for it to succeed.
Okay, R for read.
And a write quorum, W, the minimum acknowledgments needed for a write to be considered successful. Now, the crucial part is that as long as a write gets acknowledged by at least W nodes or a read gets a response from at least R nodes, the operation goes through. This means if a single server fails, or maybe even a few, the system can often still satisfy the quorum requirements and just keep operating.
That's a great explanation. So it's not just about surviving complete server meltdowns, but also about dealing with those everyday situations where a server might just be slower than usual.
Precisely. Because the system only needs a certain number of acknowledgments to proceed, it inherently gains resilience to slow nodes. If some servers are experiencing high latency, the request doesn't have to wait for them.
Right.
As soon as the read or write quorum is met by the faster nodes, the operation completes. This tolerance for partial failures and performance hiccups is a significant advantage. Definitely something to highlight when you're discussing how to build highly available systems in an interview.
Now, while these quorum setups sound pretty robust, I've also come across information about how network issues can still cause significant problems. Even if the individual database servers are up and running, a network partition could isolate clients from enough of the cluster to cause trouble. Yeah.
That's a really critical point to grasp. Network interruptions can effectively segment your database cluster, at least from the perspective of a client. Even if the majority of nodes are perfectly healthy and other clients might still have full connectivity, a client on the wrong side of a network divide might not be able to communicate with enough nodes to achieve either the read or the write quorum for a particular piece of data. So the bottleneck isn't a failed server, it's the broken communication path.
And this is where database architects face a real dilemma, right? What's the best course of action when a client can't reach a quorum because of a network problem? Do you just throw an error?
Exactly. There's a fundamental trade-off at play. One approach is to strictly enforce the quorum requirement. If a read or write quorum cannot be obtained due to network issues, the database returns an error. This prioritizes consistency.
Makes sense.
You avoid the risk of reading stale data or making writes that might not be properly replicated across the entire intended set of nodes. However, the downside is a potential hit to availability. For the clients affected by the network issue, the system might appear to be down or unresponsive.
And the alternative path involves what's often called sloppy quorums. The name itself kind of suggests a loosening of the rules. What exactly does that entail?
Yeah, you're right. It does sound a bit informal. A sloppy quorum essentially allows read and write operations to be accepted by any W nodes and served by any R nodes that are reachable at the time of the request.
Oh.
Even if those nodes aren't the designated home replicas for that specific piece of data. Think back to our server failure discussion. If a server that's supposed to hold a piece of data is unreachable, a write might still be accepted by other available servers in the cluster.
Okay, so the data lands somewhere, even if it's not its intended permanent location. How does it eventually get to the correct home nodes then?
That's where the mechanism of hinted handoff comes into the picture.
Yeah.
When the network connectivity is restored and the previously unreachable home nodes become available again, the nodes that temporarily accepted those sloppy writes will then forward the data to its proper replicas. It's like a
Oh.
temporary holding place until the intended recipient is back online, like staying on your neighbor's couch if you're locked out of your house.
Right, right. So the clear benefit of sloppy quorums is a significant boost in write availability. As long as you can find W nodes anywhere in the cluster that are reachable, you can still accept writes.
Precisely. This can be a lifesaver during partial network outages, allowing the system to continue accepting new data.
Hmm.
However, as you might anticipate, this increased availability introduces a potential challenge on the read side related to data consistency.
Right, because if the most recent write went to one of these temporary stand-in nodes and hasn't been handed off to the home replicas yet, a read request might go to the home nodes and retrieve an older version of the data, even if the traditional quorum condition, W plus RN, is technically met across the entire cluster.
That's the key trade-off to understand. A sloppy quorum doesn't provide the same consistency guarantees as a traditional quorum. Its primary goal is durability, ensuring the data is written to W nodes somewhere.
Got it. Durability, not necessarily immediate consistency.
Exactly. There's a window of potential inconsistency, where a read might not reflect the very latest write until the hinted handoff process is complete.
So it sounds like choosing sloppy quorums is a deliberate design decision to prioritize the ability to accept writes, and you're essentially accepting a potential trade-off of temporary data inconsistency. Is this a feature that's like universally turned on in all leaderless databases?
Interestingly, no. The decision of whether to use sloppy quorums is often configurable. For instance, some systems like REAC apparently have them enabled by default, which reflects a design philosophy that leans towards higher availability. In contrast, other systems like Cassandra and Voldemort have them disabled by default, suggesting a stronger default preference for consistency. This highlights that the right choice depends heavily on the specific requirements of your application.
Right.
If losing writes is catastrophic, but occasional stale reads are acceptable, sloppy quorums might be a good fit. Conversely, if data consistency is paramount, you might opt for stricter quorums. This is definitely the kind of nuanced understanding interviewers look for. You need to show you can weigh those pros and cons.
This is particularly relevant when we consider building systems that span multiple geographically distributed data centers. Leaderless replication seems like a natural fit for these scenarios because of its inherent tolerance for network issues and, well, varying latencies between sites.
Absolutely. The same characteristics that make leaderless replication robust within a single data center make it very attractive for multi-data center deployments. The ability to handle concurrent writes from different locations without a central coordinator, to tolerate network hiccups between data centers, and to cope with the inevitable latency differences across these long-distance links. Those are all significant advantages.
So, how do systems like Cassandra and Voldemort, with their leaderless architectures, typically manage these multi-data center setups? How does that work?
Well, in these systems, the total number of replicas for a given piece of data is distributed across all the participating data centers.
Hmm.
You can configure how many of these N replicas you want to reside in each specific data center.
Okay, so you spread it across the globe, essentially.
Pretty much. When a client initiates a write, it's generally sent to all the replicas, regardless of their location. However, to minimize the performance impact of potentially high latency across data centers, clients are often configured to wait for a quorum of acknowledgments only from the replicas within their local data center.
Ah, makes sense. Local quorum first.
Exactly. The writes to the replicas in the more distant data centers happen asynchronously in the background.
That makes perfect sense for ensuring a fast response time for local users while still guaranteeing that the data eventually gets replicated globally for redundancy and availability. What about REAC? How does it handle multi-data center operations within its leaderless framework?
REACT's approach, based on what we have here, seems to focus more on keeping the direct communication between clients and database nodes within a single data center. So when you configure the replication factor N in REACT, it typically refers to the number of replicas within that specific data center.
Oh, okay, so N is per DC in that model.
It appears so. Cross-data center replication and mechanisms to ensure eventual consistency across data centers are handled through separate, distinct processes. While the specifics of these processes aren't detailed here, the underlying principle remains the same, leveraging the fault tolerance of leaderless replication to ensure data availability across a wider geographical area.
So, if you're in an interview And the conversation pivots to designing a globally resilient system, being able to discuss how leaderless replication supports multi-data center deployments. Highlighting the different strategies for managing quorums and replication across these distributed environments, that would really demonstrate a strong grasp of distributed system design.
Exactly. It shows that you understand the unique challenges of global deployments, such as increased network latency and the higher likelihood of network partitions between sites, and how leaderless architectures provide effective ways to address these challenges. Being aware of the configuration options and the trade-offs involved in different systems is crucial for a senior-level discussion.
Okay, let's maybe synthesize what we've covered. We've taken a deep dive into leaderless replication, starting with how quorum configurations provide inherent fault tolerance and resilience to slow nodes.
Right, the basic core mechanics.
Then we tackled the complexities introduced by network interruptions, which led us to the concept of sloppy quorums and that critical trade-off between write availability and read consistency.
The sloppy quorum versus strict quorum debate, yeah.
And finally, we examine how leaderless replication extends to multi-data center operations, noting the different approaches taken by systems like Cassandra, Voldemort, and REAC.
And the core message for anyone preparing for those senior-level technical interviews is the absolute necessity of understanding these trade-offs. There's rarely a single best answer in distributed systems design.
Totally.
Interviewers want to see your ability to analyze different scenarios, understand the implications of various design choices, and articulate why a particular approach might be more appropriate given a specific set of requirements.
So as you continue your preparation, here's maybe a final thought to really dig into. Imagine you're designing two different systems. One is a high-throughput system for collecting sensor data where occasional dropped data points are acceptable, but the system must remain available for writes at all times.
Okay, high write availability focus.
Right. And the other is a financial transaction processing system where data consistency and durability are absolutely paramount, even at the potential cost of temporary unavailability during major network events.
Got it. Consistency is king there.
For each of these scenarios, how would you evaluate whether a traditional quorum or a sloppy quorum approach would be more suitable, and what specific factors would heavily influence your decision?
That's a fantastic exercise. Really try to map those distinct requirements onto the characteristics of traditional versus sloppy quorums. Consider the impact of stale reads, the tolerance for write failures, the overall availability goals for each system. Exploring these contrasting scenarios will not only deepen your understanding of these concepts, but also equip you to have much more insightful and, frankly, compelling discussions in your technical interviews.
Absolutely. Keep exploring these topics, think through how you would apply these concepts to the various system design problems you might encounter, and best of luck with those interviews. That wraps up this deep dive.